In this video, we're going to work example problems on gravimetric analysis. So remember, gravimetric analysis is one of the two most common techniques for studying the stoichiometry of solutions. The other common technique is titration. And so what is solution stoichiometry? Well, it's just as the name states, you're performing stoichiometry, so studying the quantitative relationships between reactants and products in chemical reactions. But with solution stoichiometry, the reaction you're performing stoichiometry on is a reaction that takes place in solution. Specifically, in this chapter, we're focusing on reactions in aqueous solution. And so a reaction in aqueous solution is any reaction to where the chemical equation or the net ionic equation, so a chemical equation that doesn't contain any spectator species, meaning that every reactant and product shown in the equation is involved in some way in the chemical reaction. And so a reaction in aqueous solution is any reaction where that net chemical equation contains at least one species that's in the aqueous state. Okay, and now, so with gravimetric analysis and titrations, we're performing what the textbook states is called quantitative analysis on reactions in solution, or in this chapter, in aqueous solution. Quantitative analysis is a term that applies to the analysis of any chemical reaction. It doesn't have to occur in solution. But in quantitative analysis, the goal is to determine the amount or concentration of a substance in a sample. So the terms quantitative analysis and stoichiometry are obviously very closely related, but they're technically not the same thing. So stoichiometry, you can think about, is the science of measuring reactant and product ratios in chemical equations. But quantitative analysis is the application of these stoichiometric principles and other measurements to find the actual amounts or concentrations of substances in a sample using techniques like titration or gravimetric analysis. Stoichiometry provides the recipe or the ratios, and quantitative analysis uses that recipe to get real-world measurements. And so that's what we're doing with gravimetric analysis and titrations. We're performing quantitative analysis on reactions in solution. Okay, so describe the basic steps involved in gravimetric analysis. How does this procedure help us determine the identity of a compound or the purity of a compound if its formula is known? Okay, so gravimetric analysis, as the textbook states, quote, gravimetric analysis is an analytical technique based on the measurement of mass. So why does it state that gravimetric analysis is only based on the measurement of mass? Aren't we going to also be measuring the volume of a certain solution mixed in or something? Well, actually, no, we're not. In general, with gravimetric analysis, the only thing you're needing to measure is mass. And so the way it works is this. So you have a substance of unknown composition. It might be the case that you know a little bit about the composition of the substance, and you're trying to figure out its full chemical formula, or maybe you don't know anything about the composition of the substance. Now, it also, as it states here, it also could be the case that you do know the chemical formula of the substance, but you can still use this procedure to analyze the purity of that substance. But at the moment, let's just think about if we have an unknown substance, and unknown in the sense that we don't know anything about the substance, or maybe we know that it's composed of chlorine or barium, but that's all we know. Okay, now, gravimetric analysis is based on a precipitate coming out of solution. It's centered around a precipitation reaction. Now, technically, there's other forms of gravimetric analysis that don't involve precipitation, but the kind of gravimetric analysis we're talking about here is precipitation gravimetric analysis. This is all going to be centered around a precipitation reaction. And so since a precipitation reaction is going to occur, and in this chapter, we're only looking at precipitation reactions that involve ionic compounds, which is the vast majority of precipitation reactions anyway, the unknown substance, and all substances involved in this process, are going to be ionic compounds, and they're going to be soluble in water. Okay, and so the idea is what you're going to do is you're going to precisely weigh out a certain mass of the unknown substance, record that mass, and then dissolve all of that in a beaker of water like this. Now, how much water, what's the total volume of this beaker solution, doesn't matter. You don't need to record this. All that matters is you precisely weighed out the total mass of the unknown compound that was dissolved. Okay, then you're going to have this other solution, they're showing here in this cylinder, this other aqueous solution that has some other ionic compound dissolved, and you're going to know exactly what ionic compound is dissolved. You're going to know all the ions that are in this solution, and then you're going to add this solution to the beaker solution, like shown here. And as a result of the mixing of the two solutions, a precipitation reaction is going to occur. You can have a precipitate coming out. That precipitate could be being formed from cations in the unknown solution interacting with certain anions in the beaker solution, or vice versa. Okay, now what's important with gravimetric analysis, with this process, is it's going to need to be the case that you're going to know the exact composition of the precipitate. You're going to know its exact chemical formula somehow. You know, if you knew some information about the unknown substance coming into this, then that could be useful for knowing exactly what the composition of the precipitate is, because again, you're going to know the ions present in the cylinder solution. And so with that, you could figure out exactly what the precipitate is. Or maybe if you didn't know anything about the unknown substance, there might be another way with a trial and error procedure, adding different cylinder solutions and performing some tests to figure out what the exact composition of the precipitate is. But you're going to need to know this for this analysis to work. Again, you're going to need to know what the chemical formula, the exact composition of the precipitate is. Okay, and so now what you're going to do is you're just going to continue to add this cylinder solution, add as much of it as you need to where the maximum amount of precipitate has formed. The maximum amount in the sense that all of the ions in the unknown beaker solution that are involved in the precipitation, all of those ions have been precipitated out. Now, you might be wondering, well, aren't we going to be tracking the volume, the total volume of this other solution, this cylinder solution that was added? I thought the only quantity that needed to be measured in a general gravimetric analysis is mass. Well, no. So, okay, in the unknown solution, in the beaker solution, you'll need to make sure that there's no solubility issues. So you'll have to take into account whatever is the potential saturation point. You'll have to be looking to see if you've reached the saturation point with the unknown species. So like it's dissolving, but then some trace amounts of the unknown compound don't get dissolved because you got to a saturation point. But thinking about solubilities of components and the associated solubility equilibrium in gravimetric analysis is a more advanced topic that we're going to look at in chapter 16. So right now in this chapter, for these problems, let's just assume that there's no solubility issues complicating the problem. So, okay, you're going to have the solution with the unknown substance dissolved in the beaker, and then in the cylinder is just going to be an excess of some other solution, some other known solution. And how much of this other solution there is, how much of this other solution that's added doesn't matter. Well, no, let me restate that. It does matter, but I'm saying it doesn't matter in the sense that you can't add too much of this solution. So like there's no, in titrations, there's like an equivalence point, right? And you want to stop right when you get to the equivalence point. Well, there is no equivalence point in a gravimetric analysis like this. Like, yes, I mean, there technically is a point where there's like a specific amount of volume of this solution that you add just enough, and with just that amount, you've precipitated that very last ion out of the unknown solution. But you don't. What I mean is, there's no equivalence point in this analysis, in the sense that you don't care about that point where the last ion is precipitated out of this solution, like you would with a titration. No, you're just going to go past that point. You want to go past that point. You've got this rod here. This is just mixing up the solution. You want to add more than you need, because all you care about is just making sure that all of the ions, cations or anions, in the unknown solution that are involved in the precipitation get precipitated out. And that has no, adding too much of this solution doesn't make any difference in that regard. Adding too little does, though. It is a problem if you don't add enough of the cylinder solution. That would be a problem. Okay, so now, once you've got the solution with all of the precipitate mixed in, the next step is to filter the precipitate from the liquid, the solid from the liquid. That's what they're doing here. Then what the precipitate that remains, you're going to want to dry it to get rid of any of the liquid solvent that is still kind of absorbed into the precipitate, the solid precipitate. And then you're going to take that dried precipitate, weigh it, and record the mass. And so there's the other mass measurement in the process. We weighed the initial amount of unknown substance that was dissolved in the beaker solution, and now we're weighing the amount of precipitate that has formed. Okay, and so now, again, as mentioned, with gravimetric analysis, it's going to need to be the case that you know the exact composition or the exact chemical formula of the precipitate. Because what you're going to do next is, with that chemical formula and with the mass of the precipitate that you measured, you can determine the mass of cation or anion, whichever came from the unknown solution that's in the precipitate. Okay, and then the key idea is, what you also know is that the entire mass of that cation or anion that came from the unknown solution that's contained in the precipitate must have come from the original unknown substance. That's the key. And so what you can then do is you can take that mass and divide it by the mass of the original unknown substance to get the percent composition by mass of that element in the original substance. Okay. Now, I do just want to point out that if you might be scratching your head a little bit thinking about how I'm intermixing the terms ion and element. I've been intermixing ion and element. Like what I mean is, I'm saying how we're determining the percent composition by mass of a certain element in the original substance. Shouldn't I be saying the percent composition by mass of like an ion instead? We're dealing with ionic compounds here, right? They're composed of ions. Well, remember that in terms of mass, the difference between the mass of an element and a corresponding ion of that element is tiny. It's tiny because the only difference between an ion and its elemental form is a few electrons at most, right? So in general, it's common when speaking about mass, you'll hear people intermix the terms ion and element, or ion and atom. All right, so that's it. The gravimetric analysis is complete. Now, you also might be asking yourself, well, this process didn't establish the entire identity of the unknown substance, right? We only determined the percent composition by mass of a certain element in the substance. So we didn't figure out the exact chemical formula of the unknown compound. But this is we still have very useful information for figuring out the full identity of the unknown compound, because percent compositions by mass of elements in compounds are going to be completely unique to a specific compound. And why is this? Well, it's because, as you know, there's no two elements in the periodic table that have the exact same mass, right? And so that's where this comes from. Okay, distilled water must be used in gravimetric analysis of chlorides. Why? Okay, distilled water really should be used in any gravimetric analysis because non-distilled water like tap water contains dissolved ions from dissolved minerals, salts, and gases, which could interfere with the analysis. But I think what they're really trying to refer to here with this question is that non-distilled water is going to contain dissolved chlorides. And therefore, if you're doing a gravimetric analysis involving chlorides, you're going to have to use distilled water. But like it could be the case for some other gravimetric analysis that you could get away with using non-distilled water because the dissolved ions in the non-distilled water could be spectator ions for that particular gravimetric analysis. Okay, a sample of 0.676 grams of an unknown compound containing barium 2+ ions is dissolved in water and treated with an excess of sodium sulfate. If the mass of the barium sulfate precipitate formed is 0.4105 grams, what is the percent by mass of barium in the original unknown compound? Okay, so yeah, this is the exact same process as everything we just talked about. We've got some compound with an unknown composition, and in this case, we know that the compound does contain barium. That's all we know. And so what we're going to do is we're going to weigh out a mass of this unknown compound and dissolve it in water. So that's the beaker solution. We're not tracking what the volume of this solution is. All we're tracking is how much mass was dissolved, and we just make sure that all of it dissolves. This unknown compound that we know does have barium in it. Right now, it says it's going to be treated with an excess of sodium sulfate solution. Here's the sodium sulfate solution. Now, upon mixing the solutions, a precipitate is formed, and we know the chemical composition of this precipitate. It's barium sulfate. We make sure we add a complete excess of the sodium sulfate solution to get all of the precipitate possible, filter out the precipitate from the solution, dry it, and weigh it, and the weight of the precipitate is 0.4105 grams. So what is the percent composition by mass of barium in the original unknown compound? Now, so in this case, this was an unknown compound. We only know that there's barium in it, but it also did mention in this first question, I forgot to answer this second part. So it says, we could use this process here to, instead of the beaker compound being unknown, maybe we know the composition of the beaker solution, but we could still use this analysis to determine the purity of that compound in the beaker. How could we do that? How would that work? Well, okay, because in that case, so we know all of the ions in the beaker solution. We know all of the ions in the cylinder solution. We know the chemical formula of the precipitate. We know the mass of the compound we're analyzing that was dissolved in the beaker. We know the mass of the resulting precipitate. And so when we calculate the percent composition by mass of the ion in the precipitate in the unknown compound, we know what to expect because we know the exact chemical formula of the compound that was dissolved in the beaker. So if it's like perfectly pure, then those 2% compositions by mass are going to match up exactly. But if the original compound wasn't pure, it wasn't pure in the sense that if this was sodium, if we were dissolving sodium chloride in here, and we weighed out 6 grams of sodium chloride, well, if there's some impurities in there, then there's not going to be as many Na plus or Cl minus ions floating around as we expect. And we'll be able to easily figure that out by comparing the percent composition by mass of whatever ion that we experimentally determined with the precipitate to what we would exactly expect from the chemical formula of the beaker compound. Okay, but again, here, in this case, we're dealing with we're trying to analyze the composition of an unknown compound that we know contains barium. So, okay, the first thing we're going to do is we know that there was 0.4105 grams of this barium sulfate that precipitated out of the solution. So we want to start by just figuring out, well, how much of this is coming from the barium, the Ba2+. Well, that's easy. What's the percent composition by mass of barium in barium sulfate. Let's determine that, and then just multiply that by 0.4105. Okay, so to get the percent composition by mass, we're just going to, let's get the atomic weights of barium, sulfur, and oxygen. So, okay, you've got barium. The atomic weight of barium is 137.33. Then plus the atomic weight of sulfur is 32.06. And then we have 4 oxygens, which have an atomic weight of 15.999. Okay, so there's the formula weight of barium sulfate, but now we just want to divide we have 1 barium divided by this. So this percentage, this 58.8% of the entire mass of a barium sulfate unit is barium, that's just saying that 58.8% of all of this is coming from the barium. So you just multiply that by 0.4105. So the mass of the barium ions were involved in this entire process that came from the unknown compound, that were dissolved into the beaker solution, and that were precipitated out of the beaker solution into this precipitate compound, like across the board, the mass of barium, I'm just going to say barium, and the 2 plus doesn't matter, just the mass of the barium element in this process was 0.2415 grams. Okay, but again, we know that all this barium must have come from this unknown compound. So what's the percentage composition by mass of barium in this unknown compound? Well, okay, just take this and divide it by 0.6760. 35.73%. There you go. Okay, the concentration of sulfate in water can be determined by adding a solution of barium chloride to precipitate the sulfate ion. Write the net ionic equation for this reaction. Treating a 145 milliliter sample of water with excess barium chloride precipitated 0.330 grams of barium sulfate. Determine the concentration of sulfate in the original water sample. Okay, so let's just start off by writing the net ionic equation for this reaction. This reaction of, okay, we've got sulfate in water, so SO4 2- aqueous. Where this came from, what original compound with sulfate as the anion was dissolved, we're not worried about. We just want to construct the net ionic equation, which, remember, that's showing you from the perspective of dissolved ions, only the dissolved species that are taking place in the chemical reaction in solution. So these sulfate ions are going to be involved in the chemical reaction. So what else? We've got sulfate in water, then barium chloride is, another solution of barium chloride is added. So we can just go ahead and let's make sure that barium chloride is soluble. It is, or else this question wouldn't make any sense. So all halides are soluble, and barium is not an exception. So there we go. So Ba2 plus aqueous and Cl minus aqueous. Okay, so there you go. There's your interacting species. Okay, so these are all of this is what we're starting with. Right when the solutions are mixed, at that instant, you've got these ions floating around. So the only potential chemical reaction that's going to occur here is between not these two. We know that this is going to, barium and the chlorine is going to dissolve, but perhaps between the barium and the sulfate. But we know that based on this question, that these are going to interact to form a precipitate. But let's double check. So all sulfates are soluble, but there's an exception with when barium is the cation. So we're going to get BaSO4 solid and Cl minus. So, okay, let's go ahead and make sure this is balanced. We've got Ba on the left, Ba on the right, Cl on the left, Cl on the right. So this is balanced. So the chlorine, the chloride is a spectator ion. So the net ionic equation is there you go. There's the net ionic equation. Okay, so now to determine the concentration of sulfate in some solution, some aqueous solution, they had a 145 milliliter sample of water with excess dissolved barium chloride. So this was added to the sulfate solution, and what resulted was you had 0.33 grams of barium sulfate was precipitated out. So with that, we want to determine the concentration of sulfate in the original sample, the original solution. All right, well, this 145 milliliters they're giving us here is just to confuse you. All that matters is that they're telling us that an excess of barium chloride was added, meaning that all of the sulfate ions in the original solution were precipitated out. We didn't run out of barium here for this precipitation reaction occurring when these solutions were mixed. We never ran out of barium. We ended up with excess. We had excess barium, but all of this was the limiting reagent. And so with that, we don't care as long as that's true, that we had an excess of the barium chloride, then this is irrelevant. What's relevant is, okay, how much of the precipitate was formed? How much of this barium sulfate was formed? It was 0.33 grams. Well, okay, no, I'm sorry. That's not, they're referring to here not how much of the barium chloride solution was added. This is referring to the aqueous water solution with the sulfate in it. And we're going to need this because we're going to need to determine the concentration of the sulfate in this original sample. So, okay, we are going to need this. So, okay, we've got, let's see, we have 0.33 grams here. This is the limiting reagent. This is the excess reagent. And so, okay, let's convert this. We just need to do stoichiometry here to get we're looking for the number of moles of sulfate ions that took place in this reaction. Moles, because once we have the moles, then we can divide moles by 0.145 liters, and there's your concentration in molarity of sulfate in the water that was tested. So, okay, to get the moles of sulfate ions that took place in this reaction that were consumed to form this many grams of barium sulfate, and this, you want to make sure that this is balanced, right? That's important. You have to have a balanced chemical equation. Well, okay, we want to convert this to moles. How many 0.33 grams of barium sulfate is, how many moles is that? So, okay, grams of barium sulfate. We need to convert this to moles. We need the molar mass of barium sulfate, and that was here, 233.386. So you have 233.386 grams of barium sulfate for every mole of barium sulfate. Okay, now we can use stoichiometric equivalencies, which states that for every 1 mole of barium sulfate produced, 1 mole of SO4 minus was consumed. And so there you go. Now that's the number of moles of SO4 minus sulfate was consumed. So let's see, we've got 0.33 divided by 233.386 0.386, 0.001414. Okay, so now what's the concentration of SO42 minus in the original water sample? Well, it's 0.001414 divided by 0.145. .00975 molarity.